Hello everybody, and welcome to our video on areas between curves. So in Calc 1, we addressed areas between a function and the x-axis, but now we're expanding this to pairs of functions, or even more than two functions. So we want to figure out how can we figure out the area between two functions that we've got a graph for. So we take a look at the functions pictured here, f and g, and we've bounded them by x equals a and x equals b. And so we ask, what's the area between these two curves and these bounds on the x-axis? So the way we construct this is basically the same way that we constructed our integral formula, or our integral definition, I should say, which is we divide up the interval into a bunch of little subintervals, and we approximate the area between the two curves with a bunch of rectangles. And so the key here is that if I take an x value, say this x value here, call it x sub I, I've got two y values that make up the top point and the lower point of the rectangle. And so this top point is f evaluated at that x sub I, and the bottom point is g evaluated at that x sub I. And so the height of that rectangle is f of x sub I minus g of x sub I. So height, f of x sub I minus g of x sub I. And of course, each of these rectangles has a width, and we call that width delta x sub I. Now, of course, most of the time we'll choose the width to be the same at every subinterval, so we don't have to write the sub I part. We can just write delta x. But the idea here is that our height times our width is the area for each rectangle. And so if we want the total sum of the area, the approximation using these rectangles, then we just take the sum of all of those rectangles, the height times the width. And that gives us the sum of the area for all of the rectangles. Now, mind you, in this example, we've assumed that f of x is greater than or equal to g of x for all x in the interval. And so that allows us to estimate the area in this way. Now, we could definitely have different situations occur. Like, for example, you could have a function, say f is this blue function, and in yellow, say this is g. And so, depending on where you are in the interval decides which function is bigger. But in that case, what you would do is you would find where the two functions cross over, and you would just evaluate each integral separately, right? Or each area portion separately. Now, of course, this sum is what we call a Riemann sum, and we should recall from Calc 1 that the definition of the integral is the limit of Riemann sums. So if I want the actual area, instead of just taking the approximation with n rectangles, I take the limit as the number of rectangles approaches infinity. And that's what we define as the integral. So all that is to say, this area between these two curves, as long as f is bigger than g, can be given by the integral from a to b of f of x minus g of x dx. Now let's summarize that in a more clear rule. If f and g are continuous and f of x is greater than or equal to g of x for all x between a and b, then a is the integral from the area, I should say, a is the integral from a to b of f of x minus g of x dx. Now, in general, the area is always the integral from a to b of the absolute value of f of x minus g of x, but most of the time we don't so much work with the absolute value as the picture we drew earlier, which is to say we split up the integral at that border where the functions cross over, and we would do f minus g on the interval from a to c, and g minus f on the interval from c to b. Now, in this case, I just want to illustrate that this delta x, right, was the width of the rectangles here. And there's one little extra detail we have to worry about. Sometimes we're going to have to integrate with respect to y because we'll have things that aren't actually functions of x. So you might have functions of y here. And so let's say you have a curve like this, and this is f of y, and a curve like this, call it g of y. Now, if this is my setup, then my interval is going to be on the y-axis. So this would be my a, and this would be my b. And when I try to draw rectangles to approximate the area between these curves, I have to draw those rectangles sideways, like this. And so that means that the width of the rectangle is actually going to be delta y. So I often get a lot of questions from students about, like, how do I know that the width should be delta x or delta y? But when you draw your picture and you draw your approximating rectangle, I think the most useful way to think about this is which axis acts as the ruler that measures the width of your interval. So what I mean is, if I'm looking at my rectangle here, and I was to line my axis up with the width of that rectangle, which axis is doing the measurement of that width? And of course, in this case, it's the y-axis that's lining up with the width of the rectangle. And in our previous example, it was the x-axis that was lining up with the width of our rectangles. Okay, so hopefully that makes that fairly clear. Okay, so example 1, sketch the region enclosed by the curves, decide whether to integrate with respect to x or y, and find the area of the region. Now, most of the time, when we are trying to find these areas between curves, we'll want to find intersection points between the curves. But in this case, I'm just going to start drawing, and it'll be pretty clear to me quickly that there's not going to be any intersections between these graphs, the sine of x and y equals x graph. But we have our bounds for x, that's from pi over 2 to pi. So we have two vertical lines for our bounds. And we'll mark 1 here on the y-axis. Now sine of pi over 2 is 1, so I'll mark that point here. And sine of pi is 0, and I know that the graph for sine is shaped a bit like this between pi over 2 and pi. Okay, so we got y equals sine of x, and now we look at y equals x. And for y equals x, when x is pi over 2, the y value will also be pi over 2. And this thing has a slope of 1, so I'm just going to roughly draw something with a slope of 1. So we see when we draw this graph, it is not going to intersect. I should say the two sine of x and y equals x are not going to intersect, so we don't have to worry about that. But when I go to draw my approximating rectangle between my curves, I have to ask myself, okay, what is my delta? Is it delta x or delta y? I'm not sure why that keeps trying to auto draw shapes. I don't want it to do that. That should not be on. Okay. All right, where were we? Okay, so here, the width of my approximating rectangle lines up with the x-axis. So that's delta x. That tells us we need to integrate with respect to x. And so my integral is going to be from pi over 2 to pi. And it's going to be my top function, which is x, minus my lower function, which is sine of x dx. And now that we've set it up, we've done the hardest part. So a couple things I want to mention before we compute this integral. I always want to see students draw this picture. For multiple reasons. One, your whole thought process is contained in the picture. What's my upper function, my lower function? What's my width of my rectangles? But also, it helps give partial credit to students so that if you were to set up this integral wrong, but I could see that something happened in your graphing that caused you to set up the integral wrong, then I can give partial credit for the computation side of things and just take off some points for maybe messing up the graph or misinterpreting the graph. Okay, so let's go ahead and take these antiderivatives. We get x squared over 2 minus, and the antiderivative for sine is negative cosine. And so this is x squared over 2 plus cosine of x, evaluated from pi over 2 to pi. And we plug in, we get pi squared over 2 plus cosine of pi minus pi over 2 squared over 2 plus cosine of pi over 2. That's pi squared over 2 minus 1, because cosine of pi is negative 1, minus a pi over 2 squared, which is pi squared over 4 divided by 2. That's pi squared over 8, plus cosine of pi over 2, which is 0. And the only thing I would do here is combine the pi squared over 2 and the negative pi squared over 4, or over 8, I mean. So pi squared over 2 is 4/8 of pi squared minus 1/8 of pi squared. So that's 3/8 of pi squared minus 1. Okay, that's it for that one. Let's move on to another example. Sketch the region enclosed by the curves, decide whether to integrate with respect to x or y, and find the area of the region. Okay, so this one is a little trickier because we don't have this first expression written as a clear function x or y equals. But what I do see is that it would be much harder to solve for y because I'd be taking a square root. And when I take the square root of a square variable, I'll actually get two functions here. So instead, I'll solve this for x, and I get x equals negative y squared plus 12 all over 4. And we'll move that over here just to save a little space. And so, in other words, x equals negative 1/4 y squared plus 12. Now, since I don't have bounds on the x-axis given explicitly, I really do have to find intersection points here in order to graph this thing properly. So I'm going to find intersection points, but also, whenever I have a quadratic expression, at a second degree polynomial, I'm going to find the vertex, right? So I want students, when graphing these things, to graph wisely. I really don't want to see students just plotting a bunch of points. That's like a big time sink. So you should know your basic functions, your sine, cosine, tangent, your polynomials, your linear functions. So your basic quadratics and linear functions, you should be able to graph those. But what I really want is just intersection points and any vertices. And if you're drawing a line, well, you need 2 points to draw a line. So as long as you have 2 points, you can just draw a line between those 2 points, and that's sufficient. But I don't want to see students just plotting a bunch of points that ends up spending a lot of time that you don't need to spend. Okay, anyway, back to it. So I want to find the vertex of this parabola. And what I know is that since this is x equals a function of y, this is going to be a sideways facing parabola. And since the term is negative in front of the y squared, I know it's actually going to look like this. And so if I want to find the vertex, that's actually where the derivative of x with respect to y is 0. So remember, when you take the derivative of y with respect to x, when that derivative is 0, you get a horizontal tangent line. But if we take the derivative of x with respect to y, when that's 0, I get a vertical tangent line. So we take dx dy, and we get negative 2y over 4, which is negative y over 2. And we set this equal to 0. And what do we get? Well, then that implies y is 0. But if y is 0, if I plug that into my original function, I just get 3. Oh, I did make a little mistake there. Oops. That said plus 12. That should have been plus 12 divided by 4, so that should have been 3. Sorry for any confusion that caused. Okay, where were we? So y is 0. I plug in 0. I get x is 3. And so this point, x is 3, y is 0, is my vertex. Okay, so I've got my vertex for my parabola, and I've also got this line y equals x. And so now I want to find the intersection points between the two curves. Okay, so how do I find the intersection points? Well, I know on one curve, x equals negative 1/4 y squared plus 3, and on the other curve, x equals y. So when those two things are equal, you'll get those two graphs crossing over each other. So negative 1/4 y squared plus 3 equals y. I'll move the 1/4 y squared across. I get 1/4 y squared plus y. And I'll subtract the 3 minus 3. Now, I could use the quadratic formula to solve this, but I see since I'm just multiplying by 1/4, I could multiply both sides of the equation by 4, and it'll still have the same solutions. So if I do that, I get 0 equals y squared plus 4y minus 12. And so that's a little bit easier of a way to find my intersection points here. Okay, with that in mind, let's see if we can factor this. Can we get factors of 4 and of negative 12 that add up to 4? And that would be a positive 6 and a negative 2. So for our intersection points, we get y equals negative 6 and y equals 2. And now, to get my x values, I just plug into either function, because these intersection points are where both functions take the same x value. So it doesn't matter which one I plug into. And of course, the easy one is x equals y here. So I get x is negative 6 for this point, and x is 2 for this one. And so those are my two intersection points. Now I have all of the critical information that I need to graph these particular two functions. Got to actually adjust the scale of that a little bit. Hold on. There we go. 1, 2, 1, 2, 3, 4, 5, 6. Okay, so we've got our two intersection points at 2, 2, and negative 6, negative 6. And the line just has to pass straight between those two things. It should also pass through 0, so my graph is a little bit askew. Let's see if I can make that a little better. There we go. And then our parabola should have a vertex y equals 0, x equals 3. So that's here. And it should look like a parabola facing to the left. Okay, so now I've got my graph, and actually I'm going to change the parabola to a different color just to make it a little bit more clear. And now I'm going to try to draw an approximating rectangle. So the height and the top and bottom of the rectangle, so to speak, have to be between the two curves. So you kind of have to turn your head sideways to see it. Why does it keep doing that to me? I didn't ask for this. Stop trying to draw lines. There we go. Keeps trying to convert things to shapes. I'm I don't see that turned on, so not sure why. All right, anyways, which axis is measuring the width of this rectangle? It's the y-axis, so this is dy. We've got to integrate with respect to y. And then the question becomes which function is bigger? But of course, the output is what we're concerned with. Which function has the bigger output? And in this case, we're treating both functions as their outputs being x. So we're asking which x value is bigger. And if we look at any fixed y value, if we look at this rectangle, which function has the bigger x value corresponding to this rectangle? It's the green function, which is our parabola. So that needs to be the first function in our integral. And our y values go from -6 to 2. And since we're integrating with respect to y, that's what we need is the y bounds. And so this is the integral from -6 to 2 of -1/4 y squared plus 3 minus just y. Right? Our other function was x equals y. And the next part of this is kind of standard plug and chug integration. So we get -y cubed over 4 times 3 plus 3y minus y squared over 2. And we evaluate this whole thing from -6 to 2. Okay, of course, 4 times 3 is 12. So this becomes -2 cubed over 12 plus 3 times 2, which is 6, minus 2 squared over 2. That's 4 over 2, which is 2, minus -6 cubed over 12 plus 3y, but that's going to be -18 minus -6 squared over 2. This is -8 over 12, that's -2/3, plus 6 minus 2, that's plus 4. And here we've got, well, this one's a little bit of a mess, -6 cubed. It's going to be a -216. Should probably double check that one real quick. Let's see. Six times. Yeah. So that's going to be a -216, but then there's another negative in front. So that becomes a +216, but then there's another negative here. So that becomes a -216. And then we distribute this negative to here, that's -216 over 12, by the way. And then negative of a negative, that becomes a +18. And then the -6 squared is +36 over 2. That's going to be 18, but it's negative. So this is -18. But then there's another negative distributed, so it's actually another +18. So a whole lot of mixed negatives and positives there. Okay, so let's see if we can combine all this together. 18 plus 18, that's 36, plus 4 is 40. And this is -2/3, and 216 over 12 can be simplified a bit because 216 is divisible by 4. So that becomes 54/3. And 54 is divisible by 3, so that's 18. This is -18. So that's the -18 part. Okay. So that's going to be 22 minus 2/3. And 22 is 66/3 minus 2/3. That's 64/3. Okay. Now let's move on to another example. Sketch the region enclosed by the curves. Decide whether to integrate with respect to x or y. Find the area of the region. So in this case, we've got two parabolas. We've got one parabola that's facing up, and the other has a negative in front of the x squared, so it's facing down. So the first thing I'm going to do is find my intersection points. So we've got x squared equals 4x minus x squared. So I add the x squared across, I get 2x squared, subtract the 4x. That becomes equal to 0, and I factor out a 2x, and I get left with x minus 2 equals 0. So either x equals 0 or x equals 2. And as discussed before, we can plug these x values into either function to compute the y value, because they're intersection points, so they're going to be the same. So I plug x equals 0 into x squared, I get y equals 0. And if I plug x equals 2, I get y equals 4. So those are my two intersection points. Now, I also know that 0, 0 is the vertex for my first function, my y equals x squared function, but I do need to find the vertex for my second one. And so dy dx is 4 minus 2x, and so dy dx is 0 if x is 2. And we already know the point where x is 2. We already found that y is 4 for that function. So this also happens to be the vertex for the quadratic that's facing down. Now we pick a point somewhere in our interval. We draw an approximating rectangle at that point. Right? That's just one of the many rectangles. And we go, well, which ruler is measuring the width of this rectangle? Well, that's going to be dx. And now we can set up our integral. So our area is going to be the integral from 0 to 2. That's our bounds on the x-axis. Of the top function, that's 4x minus x squared minus the lower function, which is just x squared, dx. This simplifies a little bit to 4x minus 2x squared. And this becomes 4x squared over 2 minus 2x cubed over 3, evaluated from 0 to 2. Of course, the 4 over 2 is just 2. So now when I evaluate my bounds, I get 2 times 2 squared minus 2/3 times 2 cubed minus, and when I plug in 0 to both of these terms, I'm going to get 0. So this is 2 times 4, which is 8, minus 2 cubed is 8, times 2 is 16, so this is minus 16/3. And 8 is 24/3, so 24/3 minus 16/3 is 8/3. And that's it. Moving on. Okay, so now we're going to deal with something a bit more challenging, but we'll deal with it first in the easier way, and then I'll show you how you could brute force this problem, just in case you see a problem that's a little different, similar, but doesn't work out quite as nicely as this one. Okay, so sketch the region enclosed by the curves, decide whether to integrate with respect to x or y, find the area of the region. So we've got y equals the absolute value of x, and y equals x squared minus 2. Now, the first thing that we need to know is what the absolute value of x is. Well, it's a piecewise function. That's x if x is greater than or equal to 0, and negative x if x is less than 0. The idea being if x is already negative and you multiply it by -1, now it's positive. Okay, and so what does that look like graphically? Well, it looks like two lines that pass through 0, 0. One has a +1 slope as it goes to the right, and the other has a -1 slope as it comes from the left to the right. Now, this is a quadratic, x squared minus 2, and since it's just x squared minus 2, that's just the regular x squared graph shifted down by 2. So we should know that its vertex is going to be down here at 0, 2. You can, of course, take your derivative, set it equal to 0 and all that to solve for that. But now we want to find our intersection points. And it's tricky because we have to separate this into two cases. When x is greater than or equal to 0, so that we can use this top part of the definition, the piecewise definition of the function. So if x is greater than or equal to 0, when the absolute value of x equals x squared minus 2, that's the same thing as just saying x equals x squared minus 2. And so I subtract the x, I get x squared minus x minus 2, and I factor. I get x minus 2 times x plus 1. So I get x equals 2 or -1. But of course, since we restricted ourselves to x is greater than or equal to 0, we can exclude that answer as it doesn't make sense in context. Okay, so that tells me that there's an intersection point when x is 2, and we already know that the graph of this linear function is going to pass through 2, 2, so it's going to look like this. Now I also know that the absolute value function and the parabola here that's centered, that has its vertex on the y-axis, they're both even functions. They're symmetric or mirror images over the y-axis, so I know that my other intersection point is going to be right here when x is -2, so I don't have to solve for that one explicitly. And finally, that lets me get to the process of computing the area. So I ask myself which function is larger, so I'm integrating from -2 to 2, and the larger function here is the absolute value of x, and I'm subtracting the x squared minus 2. And I didn't draw my rectangle this time, but I should. Of course, my top function is the green function, the absolute value. And my width of my rectangle is being measured by the x-axis. Now, the tricky part here is if I want to integrate the absolute value of x, I actually have to split up my integral on this bound for x greater than or equal to 0 and x is less than 0, so that I can use each version of the definition on each appropriate domain. But because these are even functions, when we take the integral of an even function from -a to a, we can bypass that a little bit and just double the integral from 0 to 2. And that's great because if my interval is from 0 to 2, then I know the absolute value of x is going to be strictly positive, and I can drop the absolute value symbol at that point. So I can write 2 times the integral from 0 to 2 of x minus x squared plus 2 when I distribute the negative. And now I take my antiderivative, I get x squared over 2 minus x cubed over 3 plus 2x, evaluated from 0 to 2. That's going to be 2 times 2 squared over 2 minus 2 cubed over 3 plus 2 times 2 minus the integral, or minus this expression evaluated at 0. But all of these go to 0 when I plug in 0. So this is 2 times 4 halves, which is 2, minus 8/3 plus 4. All right, so what are we going to get here? 2 times 2 plus 4 is 6, and I want to convert that to thirds, so it'll be 18/3 minus 8/3, that's 10/3. And double it, that's 20/3. Okay, so that's how we can use symmetry to make this a fairly easy integral. But you might have functions like an absolute value that's shifted over the y-axis, in which case you might not be able to use that kind of symmetry in those problems. So just to illustrate, I'll just do the first step of setup. I'm not going to work through the whole thing because we've already worked it out and worked out a solution. But if I have the absolute value of x minus x squared minus 2, that was, I didn't copy that wrong, did I? Nope, that's right. Since this absolute value of x changes definition at 0, I can split this integral up from -2 to 0. And I'm also going to distribute that negative so I don't have to write that every time. Plus the integral from 0 to 2. And then I can use the definition for the absolute value of x on the appropriate domain. From -2 to 0, this thing should look like -x. So this becomes the integral from -2 to 0 of -x minus x squared plus 2 dx plus the integral from 0 to 2 of positive x minus x squared plus 2. So I encourage you to try finishing that one on your own, but you should get exactly the same answer if you do. Okay. Now let's move on and do one more example. So as I mentioned earlier, usually we'll be dealing with areas of regions bounded by 2 functions, but sometimes, of course, that's like an artificial restriction. That's just what we practice a lot in this section. But sometimes you might be dealing with a region bounded by 3 functions. And of course, that complicates things a little bit. So that's what we're going to do. We're going to find the area of the region bounded by these 3 functions. And as always, we're going to have to find some intersection points and all that stuff. So the first thing I'm going to do is find the intersection points between my lines, because that's going to be the easiest. And then this over here is the square root function multiplied by 2. So it's just a vertically stretched square root. But yeah, we'll start with our intersection points. And since we have multiple functions here, we want to be super clear which ones we're doing. So since I marked these in purple, that should make it clear. -x plus 8 equals x over 3. So I add the x across, I get 4/3 x, subtract the 8, minus 8 equals 0. Well, I shouldn't have subtracted the 8 there. It's going to be easier to just solve it by dividing. So multiply by 3, divide by 4. That's 24 over 4 equals x. And that's going to be x is 6. And if x is 6, let's plug that into the second one. Y equals 6 over 3. So y equals 2. That's my first intersection point between the 2 lines. And let's see what that looks like. All right, so that's my first intersection point. Now, this y equals x over 3 also passes through 0, 0, because there's no plus b here, right? So the y-intercept is b. So that passes through 0, 0. So that's just this straight line here. Slope 1/3 passing through 0, 0. Now this line, y equals -x plus 8, that's going to have slope -1. And so I can plot a second point just by using that. Going over 1, up 1, so that I have a negative slope. So this second line should look like this. Now, this square root function, I happen to know it passes through 0, 0, so that makes things pretty easy, right? It's pretty obvious. I plug in 0, I get 0. So this passes through 0, 0. And so that actually tells me that there's an intersection point between the square root and this function x over 3. And I know that when I plug in x equals 1, I'll get 2 times the square root of 1, which is 2. I'm only plotting that 1 point just to get the shape. This graph I know is going to be coming up in this direction. Let me switch colors here. But I want to make sure I get the intersection point right with the rest of the graphs. So even though this one was easy, I need to know, does this intersect with my purple graph here, the negative x plus 8 graph? So if I take the 2 square root of x and the negative x plus 8 as my second check for intersection points, well, what can I do? I can square both sides to get this, instead of being the square root of x, to get it as a power of x, which will let me solve it. And so what do I get? I get 4x for squaring the left side. And then this is, I'm going to write as 8 minus x squared, same thing. That's 64 minus 16x plus x squared. And I subtract the 4x. And so this gives me, I'll rewrite this again, x squared minus 20x plus 64. So then I want factors of x squared minus 20x plus 64. So I'm looking for factors of 64 that add up to negative 20, which would be negative 16 and negative 4. This gives me x equals 16 and x equals 4. Okay, and so if x equals 4, that puts us up here on this point. And so our graph looks like this. So this purple graph, that's y equals negative x plus 8. The red graph, that's y equals 1/3 x. And the green graph is y equals 2 times the square root of x. So now, basically, all I need to realize is that I have to split this into 2 problems, 2 integrals, at this meeting point between the 2 functions. All right, so at this point, when x is 4, I can integrate the left side using the green function as top and red as bottom. And then from 4 to 6, I integrate using the purple as my top function and the red as the bottom function. So I need 2 integrals, the integral from 0 to 4 of 2 times the square root of x, which is x to the 1/2 power, minus 1/3 x dx, plus the integral from 4 to 6 of negative x plus 8 minus the 1/3 x. And now we just compute. So this first integral is already in the perfect form. I add 1 to my power. That gives me x to the 3/2 divided by 3/2 minus 1/3 x squared over 2. And we evaluate that from 0 to 4. Plus this one, I'm going to combine my x terms before I try to integrate it, just to make it a little cleaner to work with. So we've got positive 8 minus 1x minus a third of x. That's minus 4/3 of x. Now I'll simplify this first expression a bit. 2 divided by 3/2 is 4/3. I got to multiply by the reciprocal there. So that's 4/3 x to the 3/2 power. And instead of writing it as x to the 3/2 power, I'll change that to radical form as the square root of x cubed minus 1/3 times 1/2, that's 1/6 x squared, evaluated from 0 to 4, plus. And now the second integral, that's going to be 8x minus 4x squared over 3 times 2, which is over 6, evaluated from 4 to 6. Okay, so this first evaluation, I plug in 4, that's 4/3, times the square root of 4, which is 2 cubed, minus 1/6 times 4 squared, that's 16, minus, and then I plug in 0 to both functions, so I get 0, plus 8 times 6 minus 2/3 times 6 squared, minus 8 times 4 minus 2/3 times 4 squared. And now we just got to clean up these numbers a bit. So we've got 2 cubed is 8 times 4, that's 32/3, minus 16 over 6, which is 8/3, plus 8 times 6 is 48, minus 8 times 4, which is 32. So I should get 16 from that, minus 2/3 times 36, which is 2 times 12, which is 36. Wait, no, it's 24, sorry. So let's try that again. 6 squared, 36, divided by 3, it's 12, times 2, it's 24. There we go. And then we've got a negative of this negative, so that should become a positive. 16 times 2, that's 32/3. All right, now we've got 32/3 plus 32/3, that's 64/3, minus 8/3, that's 56/3, minus 8. And 8 is 24/3, so that's 56 minus 24. It's 32/3, barring any silly arithmetic mistakes. Okay, and as far as this section goes, I think that's pretty much as hard as any of these problems get. So if you can do that, you can do anything. All right, well, that's it for this section. Thank you for watching.